Welcome to the Healing Guardian channel. We are going to discuss biostatistics in relation to medicine and public health. We are going to look at data and its types, how to describe data and summarize information, understanding population versus samples, probability and distributions and how it is used to predict outcomes, hypothesis testing, and how we make decisions after collecting data, comparing groups to see whether there is a difference, especially after trials, and we'll look at association and prediction, how we identify whether one component is associated with another. So the aim of this video is to break down the complex ideas, to use simple and real-world examples, focus on understanding but not memorizing, and to empower you to interpret research, putting in mind that there are many components and software tools that can be used for biostatistics. But what it is most important is understanding the science behind it and its application. Biostatistics is the application of statistical methods to biological and medical problems. That is what makes it bio. We are looking at statistics and statistical methods. We are using them to interpret biological and medical problems, what someone else will call reasoning with evidence. Reasoning with evidence. You get the data, summarize it into information. Use the information to get knowledge, which will enlighten you on which decisions to make. So it takes you to what is its relevance, especially in medicine or public health. Number one, understanding research papers, diagnostics, treatments, and prognosis. Many times, research papers present data in form of tables, in form of graphs, in form of illustrations, and making sense out of them requires some biostatistics. Actually, without biostatistical knowledge, you cannot interpret them. Interpreting clinical trial results. Imagine a new drug comes out, you want to test whether it is effective or not. Meaning, after the clinical trial, you need to do biostatistics to prove or to make evidence-based decisions. The knowledge of biostatistics is used in conducting research because you will know that which mistakes or which factors can affect your research process that will in turn affect the data you have collected and how it is used. So that knowledge enables one to know which measures and precautions to take during research and which areas to take more concern in. Lastly, it is critical for evaluating health information. If new interventions have been made, new policies, news has presented data, we use biostatistics to evaluate this health information, whether it is worth or not. To start with, we start with the building blocks because in biostatistics we are dealing with data. So understanding data is a prerogative to understanding biostatistics. Data refers to measured facts or recorded information. Whenever we go out conducting a research, especially medical research, we are collecting data. This data, we can divide it into three parts. We talk of observations. Those are the sample or population. You may record down the people you have recorded, the people you have interviewed. That is data, that is observations. We talk of variables, which are the characteristics we are measuring. So we are in a population sample, we are measuring age, we are measuring weight. That is a variable. It is also a part of data. All that is raw material. And lastly, we have the values, which are the figures. You are measuring weight. What did you get at 65? That is data. You are measuring blood group. What did you get? I get A, B, O. That's data. So those are the three main parts of data. And basically, data is raw material in biostatistics. Data is just the starting point. Data can be categorized into mainly two. Is it quantitative or qualitative? Quantitative data are numerical values that can be measured and used for calculations, meaning we are representing them in numbers or figures. You calculated age, you record it in figures. Blood pressure in figures, weight in figures. So one of the key identifiers of qualitative data, it is numerical in nature. And number two, it can be used in calculations. Unlike we have qualitative data, which is categorical. Qualitative, we are described in categories or qualities. For example, this illustration here, you ask someone, how do you feel about this? Say, I feel like this, I think this, I feel this. That is qualitative. Many times it is subjective. Qualitative data, you measure what is your gender. I am male, I am female. The data you have recorded cannot be used in math equations. So it can only be called qualitative. Still, in understanding data, the type of data determines the scale of its measurement. The scales of measurement, they tell us how data is classified and which statistical methods to apply to them, as we'll expound later. The graphs you use, the tests you use are determined by the type of data you are dealing with. And we mainly use three main scales. We talk of the nominal, the ordinal, and the quantitative, which is also actually basically we may call them four. Because in categorical data, we have two scales. In quantitative data, we have two scales. So in categorical data, we have the nominal scale, where what you are measuring cannot be, what you are recording cannot be ordered or to be put into degrees. The example has been given as blood type. You cannot say that blood type A is greater or comes first before blood group B, because they are not directly comparable in terms of amount. That is what we call it nominal. They are mainly about putting into groups that what is your gender, male, female. But in categorical data, we also have ordinal, which are ordered categories. The data you are recording can be recorded in degrees. That how do you feel? How severe is the sickness? That it is mild, it is severe, or this is weak, this is strong. That is ordinal data. Still, we cannot use it for calculations, meaning it is qualitative, but it can be put in degrees. If you talk of the school level, primary, secondary, tertiary, ordinal data. In quantitative, we have two scales. We either use the interval scale or the ratio scale. And the main differences is that the interval scale, the interval scale, the interval scale does not have a true zero. Of course, in all of them, they have equal time intervals. And a good example is in interval scale is temperature. Yes. Because 0 degrees Celsius in temperature does not mean there is no temperature. That is what I mean that there is no true meaningful zero. In other words, they mean that zero does not mean absence. Unlike interval scale, we have the ratio scale in quantitative data, where the values that have been recorded, first of all, while it is called a ratio scale, the values can be compared in terms of amounts. If I have measured your weight and this boy is 60 kilograms, the other boy is 10 kilograms, I can say that this one is 6 times heavier than the other one. That is different from the interval. Just because I'm looking at figures in temperature in the interval scale at 20 degrees Celsius, 10 degrees Celsius, but in reality, it doesn't mean that one of 20 degrees Celsius is twice as hot as one of 10 degrees Celsius. So ratios don't apply in interval. Values cannot be compared in amounts. That is why the other one is called a ratio scale. Another example can be blood pressure in a ratio scale. I can say that someone with 60 millimeters of mercury has a blood pressure which is twice that one of 30 millimeters of mercury. That is a ratio. And another last difference is that in a ratio scale, zero means absence. If you have 0 millimeters of mercury, you have no pressure. If you have 0 kilograms, you have no weight. But in interval scale, 0 does not mean absence. Lastly, in understanding data is the variables we talked about. A variable is a characteristic you are measuring. Those variables can be grouped into two, those which are dependent and those which are independent. And to understand it simply, like in the case of public health, an independent variable is considered to be a cause. If you're looking at a relationship, or what you're calling an input, so that you see an outcome. In other words, you can call it a factor you change or observe to see its effect. If you're looking at the relationship between smoking and lung cancer, between the two, which one are you considering the cause? Of course, it will be smoking. Smoking will be the independent variable. And another way of putting it, that the factor that you increase, in other words, to see an effect, is an independent variable. The exposures many times are the independent variables. And the dependent variables is the opposite. It is the effect. As you have been looking at smoking, what is the effect? Lung cancer. Cases of lung cancer, those will be the dependent variables. They are depending on the exposure. Or if you don't call it an effect, you can call it what are you measuring in response. You have increased this one, so the idea is to see what you want to measure is the dependent variable. From there, we go to describing data. We look at what does it look like. We have started with the building blocks, which is data. In describing data, you want to see what does the data look like. What is its shape? What is its center? What can I call the center value of, if I've recorded blood weight, what can I call the body weight? What weight can I call to be the center? That is what you call, we also use it in describing data. And lastly, how spread out is the data? How spread out is the data? Where are the outliers? Those are the three things we are looking at. So in looking at what your data looks like, we mainly use data visuals. That is number 3. So imagine you have gone out in a survey, you have gone out in a research, you have collected a lot of questionnaires, a lot of forms. You need to sit down and get this data and make it into meaningful information which can be interpreted. That is basically what you are calling describing data. So the first thing, we have measures of central tendency, measures of spread, and data visuals. Those are the 3 things we use in describing data. Before describing data, one of the tools that is very important is making a frequency distribution table. And as the name suggests, the frequency distribution shows how often each value or group of values appears in a data set. We are looking at how is the frequency distributed. If it is body weight, how many people have 70, how many have 71, how many have 72. Then you draw it into a table. You show the frequency and the values recorded. That is what a frequency distribution table means. It is useful for spotting trends, creating charts like histograms or bar graphs, because we get this frequency table and we use it to make the graphs, and understanding data distribution at a glance. Because just looking at this table, you can see the mode, that this one has the highest frequency, meaning the mode is relying in this range, or this is the mode. It also shows you a glance of the spread. Most of the values are concentrated here. So we use this frequency distribution to determine the rest of the measures we use in describing data. To start with, we can talk of bar charts and pie charts. A bar chart, we use rectangles to show the size of each category, where the height shows the frequency of that category, and it is good for comparing categories side by side. Its unique quality of a bar chart is that the bars have to be independent. So it is important to note that bar charts and pie charts are mainly used in categorical data, that is nominal and the ordinal, because many times categorical data is independent of each other. That is why we are drawing bars. If it is in a bar chart, they should be independent. It shows you the relation. You can be used to compare that if these are the males, how many males had lung cancer, how many females had lung cancer, then you draw a bar chart. So you can easily compare using your eyes. The longer the bar or the higher the bar, the higher the frequency. Unlike that, a pie chart, the advantage it has over the bar chart is that it shows you the proportion. If I'm comparing 5 qualities, which one is more than the other? It shows you better the proportions, because you draw the pie, the size of the slice shows you how frequent or the size of the value you are looking at. Histograms are mainly used for quantitative data, because many times quantitative data, especially the continuous one, because for discrete data it will be, if it is counting anyway, both the discrete and continuous. But many times histogram is mainly applicable to the continuous data. That is why its bars have to be in contact with each other to show continuity. Each bar in a histogram is showing a range. Yes, a range or a certain value that's between 100 and 120, between 120 and for the sake of continuity, the bars have to be close to have to touch each other. And before we leave it also shows you the spot patterns or the shape of data. Because if you look at your histogram, on the y-axis you're having frequency, meaning if you have most of the bars are concentrated in one place, that is already showing you the spread, meaning that the data is more clustered here. But it can also show you the distribution. Is it normal? Is it skewed? Is it more to the left? Is it more to the right? Also, that information can be got from the histogram. Measures of central tendency. So at first we are looking at data visuals. You are describing data by using visuals. And we also talk of box plots later on. In measures of central tendency, we are basically using numbers that can describe the center or average of a data set. And this number we are looking for is what we call a typical value. There are 3 types of measures we can use to look for a center. Like you measured the blood pressure, you measured body weight. Which value can you use to determine that this is the center of body weight, this is the average in my population? We can use the mean, the median, or the mode. The mean is called the average, and as usual, get the total values, divide by the total number, and you get the average. The median is the middle value. Many times we just order the values in ascending or descending order. The value in the middle is the median. If the data set is even, then you look at the 2 values in the middle, you get their average. That will be the median. The mode shows you the most frequent. If it is a distribution with only one mode, actually the histogram can easily show you the mode. But sometimes you have distributions with more than one mode, like a bimodal distribution or a multimodal distribution. But in the mode, we are looking at which value appeared most frequent. So all of these 3 can be used to measure central tendency. So the question will be, when do I use this? When is this one most appropriate? It determines on the appearance of the data. In asymmetrical data, symmetrical, that is, if it is normal distribution, the mean will be the best expression of the central tendency. That's why many times when you are dealing with populations, since most natural phenomena follow a natural distribution, a normal distribution, the mean is the best measure of central tendency. But sometimes in some distributions they are non-symmetrical. Like we talk of skewness, being right skewed or left skewed. In this case, the median becomes the best for measuring central tendency. The example I can use is this we used here. We are having mask here. Maybe you conducted a research in USA. You want to determine what is the average income of a citizen of USA. Then you go and you measure the average income or net worth of all the people in USA. You'll find that there are those outliers. There are those little few like Musk who are at extremes and they have a lot of money. So if you use the average income of all people in USA, it will not be the best estimate for the central or typical value for that population. Because if someone having $1 billion, you are using that value to measure the average with someone earning $10,000. You may get the average maybe like $1 million, and you say the average person in USA earns 1 million, yet it is not realistic. But in that case, the median will be the best because since most people are earning little, their middle value will be the best for estimating the median, the central income, or say, okay, average income. So in that case, that is what we are talking about. If the data is skewed, median will be the best for measuring central tendency. And lastly, the reason is the mean is pulled by extreme values. If you're having strong outliers, maybe someone with very high or someone with very low, if you use all their values to measure the average will not be a realistic representation. That is central tendency. Measures of dispersion, they show how spread out data points are. They are important because they reveal consistency, different spread, even with the same average. There are some data sets which have the same average, but it does not mean that they have the same dispersion. You can measure a certain population, maybe you're measuring weight in a certain village and weight in another village. Just because they have the same weight does not mean that the dispersion is the same. We need to know how spread out are the data points, and we use mainly four values: the range, interquartile range, standard deviation, and variance. So this is what this graph is illustrating. That if most of the values are close to each other on the graph, if this is an histogram, it will be represented like this. But high dispersion, you're having many values are spread out from each other, so the frequency is somehow distributed. So they can be when both of these, we are looking at the same number of people were used. We measured their average when it's the same, but we measure the dispersion and it is completely different. So we use these measures to determine that. First, we talk of range and interquartile range. The range is the simplest measure of spread. You simply get the highest value, that's the person with the highest value, minus the person with the lowest value. So it is like it is giving you the total span, one extreme and another extreme. So these two values, they are showing you where all the population is lying. Meaning the bigger the range, it means you are having someone with very high and someone with very low. So it can be easily skewed by outliers. What this means, that if you get someone with very high and someone with very low, the range increases a lot. And it may not be representative of the rest of the population. Because if you find that most of the population is in the center, but you're trying to measure how spread out it is, then you use the range. You may find the range is very big and you think the data points are so spread out, yet actually there are these outliers which are pulling it. So in this case, the best measure for showing spread would be the interquartile range. It measures the spread of the middle 50% of your data. It is the difference between the 70th percentile, which is the same as third quartile, and the 25th percentile, which is the first quartile. So many times when you're measuring spread, you may use a number like remember spread, we are looking at how spread out are the data points. This number line may be divided into 4 quarters. You have the first quarter, second quarter, third quarter, fourth quarter. However much we have 4 quarters, we have 3 quartiles. The first quartile is the value that represents where the first quarter ends. The second quartile shows you where the second quarter ends. The third quartile shows you where the third quarter ends. So these are the 3 quartiles. In brief, the second quartile is actually the median because it is in the middle. Where the second quarter is, that's a half. That is why in another name we can call the median a 50th percentile. If I'm looking in percentages, 50%, that is the middle. In quartiles, second quartile, that is where the second quarter is, that is the middle. So interquartile range, remember in ranges we are getting differences. What is the difference between the third quartile, meaning where 75% ends, minus where 25% was ending? So I'm looking for where the middle 50% of the population is lying. That is why you're using this calculation. Get Q3, which is this, minus Q1. And actually this is a box plot, but we'll expound on it. So as we have said, it is a better indicator of spread because it ignores the extreme values. The extreme values do not pull it a lot compared to the range. Variance and standard deviation. Many times variance and standard deviation, which is what we are going to apply most, is what we apply most in biostatistics, in dealing with research and the inference statistics. Variance and standard deviation, we are using the mean to measure the spread. So we take it that the mean is in the middle. We mainly use it in normal distribution. The mean is in the middle of the population. So we use the mean to measure how far are other figures from the mean. You get it? So standard deviation is a measure of how far a certain figure, the distance of a figure from the average. So variance is called the average of the squared differences from the mean. So what we do in variance, I will get all the values I've recorded. I use them to measure the average. After getting the average, I get the difference between each value and the average, each value and the average. Then I square all those differences, then I find the average of that sum. So I add all the squared differences and I divide by the total population. That is the variance. So because we are squaring, of course it also shows you the spread, but the problem with variance, the units have been squared. If I was measuring blood pressure, now I'm having millimeters of mercury squared. If I was measuring weight, I'm having kilograms squared. So we get the square root of variance to take away those square units. That is how we come up with the standard deviation. So this is the square root of variance. It provides a clear, interpretable measure of typical distance from the mean because it is expressed in the original units of data. So if I get my standard deviation as 15, it means the value I was measuring, it is 15 units from the mean. If you use that example, I measured blood pressure and the average blood pressure is 50. And I measure a certain value and say that its standard deviation is 15. It means I will get 50 plus 15 and I get 65. That is the value. Because 65 is 15 units from 50. Hope you are getting it. So standard deviation is the distance. You can call it as the distance, typical distance from the mean, at which a value is from the mean. Standard deviation is very important. Number one, it clearly shows data consistency. If we are doing the same test multiple times and the standard deviation of our data has remained the same, it means the data has been consistent. Number two, it shows you the spread. A small standard deviation means that the data points are clustered near the average. Because their distance from the mean is little, that is what you're calling small standard deviation, meaning most of them are close to the average. If you have a large standard deviation, the data points are widely spread. It allows comparison of variability. If we measured two tests from the same population, maybe if it was a randomized control trial, we look at the first data set we recorded and the second one, see that as the standard deviation changed, if the standard deviation has changed, meaning variation has taken place. In other words, there has been some effect. It is used in statistical analysis. Of course, as we'll see in hypothesis testing, we make almost all calculations, we use the standard deviation. Identifies outliers, and we'll talk about it here in the box plots. A box plot is a simple tool you can use to show central tendency at the same time showing spread. Because that box plot shows you the range, the interquartile range, the median, the outliers, and the spread. So it can show you all just by looking at a box plot. Many times it is called a box and whiskers plot, though it is the same thing. Its interpretation is simple. The box is representing the interquartile range. The box. Then these lines coming from it are the ones we are calling whiskers. The line in the middle of the box is the median, the middle value. Then the limits of the box are the quartiles. Meaning from this box plot in the middle, in Tauhara, this first line below is the first quartile. The second line in the middle is the second quartile, which we are calling the median. The third line is the third quartile, which we can also call the 75th percentile. Then these whiskers are showing you the spread of the rest of the data from the interquartile range. When you're drawing the whiskers, we count 1.5 standard deviations from the upper or lower quartile. Meaning if I'm going to draw this whisker, if my standard deviation is 8, I count 1.5 standard deviations. Meaning I will get 8 plus 4 to get 12. Where 12 ends from the upper quartile. Meaning I count from here up to here 12. Where it ends, that is where I draw the whisker. I do the same for below. I count 1.5 standard deviations. Where 12 ends below, that's where I draw the whisker. Then all the values beyond that 1.5 standard deviations, I plot them independently as the outliers. Meaning they are at the extremes. So you plot those data points independently. These box plots, they allow you to compare data sets. For example, as we said, two data sets may have the same average, but same median, but when the rest are different. They may have the same average, but when the rest are different, the box plot will show it to you. So as I've said, this box here, the lower quartile will be here. So it is around 25. The upper quartile will be 100. The median 40. Then the outliers, if you look here at Hot Hill, these are the ones that have been plotted independently, meaning those are the extreme outliers, but you can also have them below, down if there are any. So that's what this text is explaining. Skewness and kurtosis, we also use it to describe data, and we already introduced it earlier. Skewness indicates the asymmetry of the data distribution. A positive skew means the tail extends to the right. You should note that skewness, we are looking at the tail. Meaning if data is positively skewed, it means the tail is to the positive. In other words, positively skewed is the same as saying right skewed. Then negatively skewed is the same as saying left skewed. So skewed data is data which is not symmetrical. And if we say that the skew is 0, it means the data is symmetrical, like a normal distribution. It means there is no either right or positive skew. That is what skewness means. Kurtosis, we may have data which has the same skewness. Maybe it is all symmetrical, but it is having different frequencies. We may be having the same median. For example, look at this illustration. Negative, this the middle point is the same for all these three bell curves, but the height and the spread is different. So in kurtosis, we are looking at this. We may have the same median, but we have many more people having the same median. So we may have a median of 15, but you find in this negative curve, maybe 10 people have 15. In the normal curve, maybe 30 people. In the positive, 50, but when the median is the same. So that is what kurtosis is talking about. If you're looking at maybe recovery times, you have done a clinical trial, kurtosis will tell you how peak, what we call leptocuric, the peak, meaning like this positive one is peak. We say that it is leptocuric. Platicuric is how spread out, like when you see at this negative one. You may find that in the leptocuric, like this positive one, if you're looking at recovery times, most people recover at the same time. But in the negative one, you find that people are recovering at diverse times, having a curve which is platicuric. Z scores, they are also used to describe data. We are using the concept of standard deviation to make Z scores. A Z score measures how many standard deviations an element is from the mean. Z scores are very important in hypothesis testing because we are comparing data which may have different scales. So what we do, we transform all data we have recorded into a standard scale. In terms of Z scores, that is what we call standard data. So what a Z score means, a Z score means how many standard deviation is this figure from the mean. So even if we have different means and different standard deviations, we are looking at the number of standard deviations from the mean. So if I get a certain value and its Z score is 1, it means it is one standard deviation from the mean, whatever the standard deviation is. If it is 2, it is 2 standard deviations from the mean. That is what the Z scores are telling you. So a patient's weight might be 70 kilograms, but you want to say is that high or low for their age and height. So a Z score tells you how far the weight is from the average weight for someone similar, putting it into context. A positive Z score means the data point is above the mean. Negative Z score, it is below the mean. A Z score of 0 means that the data point is exactly at the mean. Of course, 0 means that there is no distance from the mean, so it is the mean itself. So how do you calculate the Z scores? You subtract the mean from the data point and divide by standard deviation to find how many. In brief, if you're subtracting one data from the mean, I'm looking at, if I look at this distance from the mean, how many standard deviations are there? What you get, you record it as a Z score on this number line, either 0, -1, 1, 2, 1.5. Then we can end with a concept of scatter plots in describing data. Each point on a scatter plot is a pair of values of two variables. Maybe we are trying to relate, is there a correlation between age and blood pressure? So you go and make maybe a cross-sectional study and determine how many people. Okay, you make a questionnaire, let me say, what is your age? You measure the blood pressure, your age, blood pressure, age, blood pressure. You collect the data, you plot it as a scatter plot. We use these scatter plots to show whether there is any correlation. So they are excellent for visually identifying the type of correlation and its strength. So it directly brings us to correlation. Correlation means the measure of strength and direction of a linear relationship between two quantitative variables, and basically linear. Meaning if you plot the data points and they don't form a line or they don't form any linear relationship, we say that the correlation is zero, or there is no correlation like this graph. The correlation coefficient ranges from -1 to +1. Usually in calculations, instead of using your eyes to see the correlation, we calculate it and we use data tables to see how strong is the correlation. Is the correlation negative? Meaning even if you have not plotted the scatter plot, you can find the correlation using correlation coefficient. What does positive and negative mean? Positive correlation means that when one variable increases, the other one also increases. The opposite is true. If one value increases while another one decreases, we say that they have a negative correlation. Important to note, correlation is not causation. A good example might be ice cream sales, and you are looking at shark attacks. That ice cream sales and shark attacks both increase in summer. That means they are correlated, but does not mean that one is causing the other. Doesn't mean that the more we sell ice cream, the more the sharks are attacking us, so we should stop taking ice cream. So that is a correlation. But a causation, we only call it a causation if the variable increases is the one that is directly producing a change in another variable. So many times we have confounding factors like this illustration is showing you. Someone else may measure ice cream and sunburn. That during summer, we're having high cases of sunburn. At the same time, people are taking a lot of ice cream. Don't you think ice cream is causing a sunburn? But that simply means they are correlated. We can only prove association by using the tests of association, which we'll look at a later time. Okay, in front, we look at how do we measure association using tests. So in this case, it is actually the hot sun. It is causing people to take a lot of ice cream, and it is also causing sunburn. In that case, we will call it a confounding factor. So correlation is not causation. Having talked about data and its types, and we have talked about how we summarize data into information, now we go to the real thing of sampling and probability. Many times when you are conducting research, when you are collecting data, we have to pick samples. So just by the matter of picking samples out of a big population, it brings in probability. Because what if the people you selected, what if you selected them in a wrong way? Or after you have collected data, you're trying to say that since my data, the average is this. You want to say now the average of the rest of the population is also the same. So it brings in probability and sampling. And ideally, you cannot separate probability from biostatistics. The first concept begins with a population and a sample, because you are sampling from a population. The population is the entire group you want to draw conclusions about, what we call the target population. So it is your big picture of interest. Maybe you're interested in measuring, maybe let me say blood pressure among the women in Wakiso district. That is your population. But now you have to pick out samples out of that. You can't test every person, let me say in Gulu, for malaria. So if you're looking at malaria cases in the population which is Gulu, we need to pick out samples. So you test a smaller and a representative group, what you're calling a sample. The sample has to be smaller and it is a manageable subset chosen from the population. So we need to test from these samples we have picked so that we make conclusions about the rest. Why do we sample? The reasons are many. We talk of impracticality. Like we have talked of, if you are measuring malaria cases in Uganda, you will not measure every person in Uganda, so it is impractical due to the large size. Sampling saves time. Even when you have the resources, it consumes a lot of time, which may be unnecessary. Sampling reduces costs. Instead of testing 1,000, just test the 100 and use them to make inferences about the big population. It is manageable. Many times it is impossible to measure the whole population, like in destructive testing. You are testing a new drug. How will you test it on everyone? So you have to pick out samples which have to be representative. Then they give you an insight about the rest of the population. There are certain techniques we use in sampling in biostatistics. We may talk of random sampling or non-random sampling. Random sampling is preferred, and many times we use non-random sampling where random sampling is not effective or is not ideal. In random sampling, every individual has an equal chance of being selected. That means your sample will be representative because everyone in the population had an equal chance, meaning you have combined, you have reduced a lot of bias. Random sampling reduces a lot of bias. So many times if we are making research, scientists would prefer relying on a sample that has been made from random sampling because all people have equal chances and it is representative enough. It is easy to generalize results which you have made from random sampling than from a non-random sampling. Examples of random sampling: 12 simple random sampling. That is, you get the whole population, you get the whole list, and you determine the sample size and you pick randomly. That is, you choose randomly. Maybe you get a list, then you run randomly, assign abstract numbers, and anyone can be chosen, irrespective of your judgment. Stratified sampling, you go to a certain population, you want to pick a population which is representative enough. So you look in this population, you break it down into subgroups and you sample those small subgroups. If it is a hospital, you identify which stratas are there. Maybe we have the cleaners, we have the nurses, we have the doctors, we have the patients. And you are trying to make a survey in this hospital. So you will say that, let me get the list of the nurses. I perform a random sampling. I pick out. I go to the doctors, I perform a random sampling. So in every strata, you perform a sample. Systematic sampling, you follow a certain order. Maybe you get the whole list of patients in the hospital. Then you say, I'm going to pick person, every fifth person in this list. So you go on picking the fifth, the fifth, the fifth. If you have gone to a market, say that every 10th person I find, I will interview. So you are following a certain order. That is why you call systematic. In random sampling, lastly, we can talk of multi-stage sampling. You perform random sampling at different levels. First of all, maybe you want to look at prevalence, prevalence of HIV in the whole world. First of all, you have to choose the continents. Maybe you perform random sampling in the continents and you choose that I'm going to go on Africa, this and this. Then after choosing those, then in those continents you have to pick countries. You perform random sampling. In the countries you have to pick districts. You perform random sampling like that until you get your desired number of samples. But if you cannot do random sampling, sometimes you don't have the whole list of the people. Sometimes you don't know how many people you are dealing with. For example, you are studying a rare disease. The total number of people having it are not known or the list is not available. Then their non-random sampling is inevitable. In non-random sampling, you select based on convenience, judgment, or specific criteria. Maybe you go to the market, that I will talk to those who are nearby. That when you go to I will talk to those who I first meet. You're depending on convenience. Or those who are more approachable. In judgment sampling, you choose those who are appropriate. Maybe if you're doing a certain research that it is better I deal with politicians because they are more informed about what I'm talking about. Or you go to a hospital, instead of interviewing everyone and say, I'll talk with the top doctors, they are more appropriate. That is judgment sampling. You may talk of quarter sampling. In quarter, you determine a specific quarter or fraction you are going to choose from various groups before conducting the research. So I can say that I'm going to measure 50 males and 50 females. So I just go and I go on choosing until I get 50. I stop. So you are not doing it randomly, but I say that the first 50 people I meet, they are the ones I will record. So you made a fixed quota and you determined it before sampling. Lastly, the snowball sampling. Snowball sampling, you are dealing that one sample takes you to another sample. This one is used in cases where the rest are not known or where it may need secrecy. So you are dealing with drug dealers or what, they don't want to be exposed. So you find one drug dealer, it takes you to another one, takes you to another one. We are studying a rare disease or a rare activity that you cannot easily determine where they are. So it is like a rolling snowball. So non-random sampling is not desirable because there is a high risk of bias, beginning with the interviewer and also with the interviewee. So all these are put into consideration when we are gauging the results, how reliable they are. Starting with sampling itself, even before you have conducted the data to use it in biostatistics, sampling comes with error and bias. Sampling error is a natural random difference between a sample statistic and its true population parameter. It occurs by chance and it is unavoidable. By the matter of fact that you are sampling, there is already an error. You cannot measure the mean of a sample, it is perfectly the same as the mean of the population, meaning there is always that sampling error, which is in many cases unavoidable. But it can be reduced by the method or study design you are using. So many times, as the sample size increases, the sampling error reduces. So even the sample size you used in your calculations, in your biostatistics, determines a lot. The smaller the sample size, there is a lot of error, meaning your results will not be reliable. Then bias, which is a systematic deviation, where the sample consistently differs from the population in a specific direction. So it is systematic, meaning it is following a certain pattern. And there are many types of bias. It leads to inaccurate conclusions. We may talk of selection bias, that is among the interviewer. Whom you select, there is that bias. Because you are going to select, there are those preconceived ideas, they will influence who you select. And it is always systematic. You are biased to only one side. It can be response bias or non-response bias. You're talking to someone, maybe it is an interview, when whatever you're asking them, they're saying yes. Whatever you're asking them, they're saying yes. Or you talk of someone, you try to approach them, they refuse to answer. That is non-response bias. But what is important in sampling? In sampling, before you carry out any test, that the sample has to be representative. A representative sample is one that shares characteristics with the population. This includes gender, age, socioeconomic status, and other relevant traits. We have shown these two examples. If this is our population, you look at these two examples, this is representative, this is not. Because this sample has tried to bring out every characteristic in the population, has been represented. So if it is age, you are doing a research, include people from various ages. If you are looking at gender, include people from various gender. If you're looking at socioeconomic status, include the rich and also the poor. There, the sample is representative. That is where stratified sampling simplifies that you try to look at the various subgroups and you make sampling in every subgroup. It ensures that the conclusions drawn from the sample can be reliably applied to the entire population, because if it is not representative, we suggest that there is a lot of bias and the variability. So it is only representative samples that are efficient. So the first session we have looked at has been introducing us to now doing the calculations. We have seen that there is option of sampling, and sampling comes with error and bias. Meaning whenever we are making conclusions from results, we use probability because we cannot be 100% sure. That is why probability comes in. Otherwise, if we were sure, we would not use p-values, we would not use z-tests, we would not use t-tests. But the aim is, because we are not sure, we are using probability to prove or to compare. So an understanding of probability and probability distributions is inevitable in understanding statistics. A simple introduction, not a simple, builds the ground for the complex. Probability ranges from impossible to certain. That is from 0 to 1. Meaning if the probability is 0, it cannot happen. If the probability is 1, then it is certain. Probability helps us to make informed decisions when outcomes are uncertain, and it is the foundation of statistical inference and risk assessment, as I said. For example, you may say, what is the probability that a patient will experience a side effect, that is from a drug? How likely is it that a new epidemic will spread? Since we used the calculations which we made from samples, we use probability to assess. So it can be in fractions, decimals, or percentages, but cannot be greater than 1. The basic probability rules are the ones we use to base on to make the inferences. The first one says all probabilities must be between 0 and 1. We have already mentioned that. The sum of probabilities of all possible outcomes of an event must be equal to 1. The probability of an event not happening is 1 minus the probability that it does not happen. So if you are looking at a likelihood, at what is the probability that a patient will recover, that probability will be 1 minus the probability that he will not recover, just from rule number 2. Because when I add both of them, I have to get 1. You get? When I had the probabilities of all possible outcomes, the possible outcomes, you either recover or you don't recover. So if I add both of them, I have to get 1. And that is the complement rule. Rule number 4, if two events cannot happen at the same time, the probability of either occurring is the sum of their individual probabilities. That is the additive rule. If the events I'm looking at cannot happen at the same time, remember now we are going to apply it in issues of public health. If we are comparing two events, we ask, can they happen at the same time? If not, then if we are dealing with their probabilities of happening, we sum them. Lastly, if two events do not affect each other, the probability of both occurring is the product of their individual probabilities. For example, if you are comparing smoking, maybe if you are comparing diabetes and another outcome, maybe if you're comparing two things, okay, diabetes and high blood pressure, if we assume that they are independent of each other, that the high blood pressure is not due to diabetes and the diabetes is not due to blood pressure, if they are independent, if we are looking at the chances of them happening together, we multiply their probabilities. So that is just a foundation. Conditional probability, this one applies a lot in trials, in tests, because many times we are looking at what is the probability that a patient will recover if they have tested positive. Like there is a certain condition attached. So it is a probability of an event occurring given that another event has occurred, which will write that probability that A happens given that B happens. It is crucial for understanding risk and making predictions, meaning it will come in risk assessment. probability distribution. Now we are trying to summarize because of the issue of time. Probability distribution. Probability distribution is a function that gives the probabilities of different possible outcomes. So if I'm making a probability distribution, I'll say how many outcomes. Maybe if I use a good example of tossing a coin or rolling a dice, that how many outcomes I may get: 1, I may get 2, I may get 3, 4, 5, or 6. So in that case, I will draw a table, what we call a probability distribution. What is the probability of getting 1? I put there. Probability of getting 2, I put it there. Probability of getting 3. Then after I plot a graph. So for example, this is graph of discrete distribution. This is a probability distribution. We are just recording every outcome with its probability. Outcome with its probability. In biostatistics, we are dealing with two types of distributions: a continuous and a discrete distribution. Not to forget, we started with variables, that continuous variables, they have a high range and they can be expressed in fractions and decimals. But the discrete distribution deals with counts. You are counting whole numbers. That is why discrete distribution is represented in terms of bars, but the continuous distribution we use curves. And we are going to be dealing most of the times with this continuous distribution, because most of the values we deal with in biostatistics are just measured. Talk of blood pressure, weight, all of those are continuous variables. The normal distribution is the one we use mainly in inference statistics. Why? It is because most of the natural phenomena follow a normal distribution. Normal distribution is this bell curve, and it is called normal because most of the values lie close to the mean. That is a normal distribution, what we call symmetrical. You find the mean, the mode, and the median are all at the center of the population. So many natural phenomena like height, blood pressure, they follow this trend. So if you're in biostatistics where we are using such measures, meaning we mainly use the normal distributions in hypothesis testing, it is completely defined by its mean and standard deviation. Example, say that a normal distribution of a mean 15 kilograms and the standard deviation of this, those are the ones we use to describe a normal distribution. It is very important in biostatistics. Why? Many natural phenomena inherently follow this distribution. It is foundational for various inferential statistical tests, as I've said. It enables hypothesis testing and confidence intervals, which is the last part we are now going to handle. Hypothesis testing, confidence intervals. Even for distributions which are not normal, why normal distribution is still important is that if we make samples from a population which does not have a normal distribution, or if the value we are looking at is not normally distributed, after sampling, the averages we get, they will approximate a normal distribution, irrespective of which distribution it was. So still normal distribution. That's why normal distribution is used for inference for all distributions. That is what the central limit theorem suggests. And even it says that for population distributions which are large, even if they are not normally distributed, after sampling, their averages will form a distribution which is normal. If we plot the averages from different samples, they form a normal distribution. Lastly, it allows us to standardize data. As we talked about it in Z scores, that we can use normal distribution, we get data that is blood pressure, transform it into Z scores, and treat it as a normal distribution. Helps in predicting outcomes. That is what we use in hypothesis testing. That was a normal distribution. Then what we call a standard normal distribution. Many times we deal with the standard, not the normal one, just plotting figures with their probability and we draw a curve. No, we use a standard one, which I already introduced. What we call a standard normal distribution, or a Z distribution, is a normal distribution with a mean of 0 and a standard deviation of 1. Meaning when I draw my bell curve, in the middle there must be 0, that is the mean. And the standard deviation is 1. So these white lines you are seeing, these are standard deviation lines. That from 0 to -1, that is one standard deviation. -1 to -2, another standard deviation. -2 to -3, another standard deviation. As we said, negatives means that the values are going below the mean. Positive means the values are above the mean. And a normal distribution can be transformed into a standard normal distribution using z-scores. And this is the calculation we are talking about, that I get that value, which is x. I remove the mean from it to get the difference there, then I divide by standard deviation to find how many standard deviations are there between. So they have shown this example. The mean is 5. We are having here a value which is 8. Maybe this is 8 kilograms. The mean is 5 kilograms. The standard deviation is 10. If you are making it standard, you said you get the mean, the value minus the mean divided by the standard deviation. So where there is the mean, if I get 5 minus 5 divided by 10, I get 0. That's why I say that in a standard normal distribution, the mean is 0. Then where we had 8, I'll get 8 minus 5 divided by 10, because I want to determine how many standard deviations are in between here. So I get 8 minus 5, I get 3. 3 divided by 10, I get 0.3. I have standardized. That is what we call standardizing. Besides normal distribution, just to mention, we also have binomial and Poisson distribution. Binomial distribution, we use it when you are dealing with successes or trials. For example, if you are doing a clinical trial, you have performed a test 10 times, then you find out what is the probability that a person will heal, or that the test will be successful 7 out of 10 trials. There you are dealing with successes and failures. That is why I say that in binomial distribution, you only have 2 possible outcomes, either success or failure. So we are dealing with number of successes. That is, if the test you are carrying out, you are looking at the successes. But in Poisson distribution, you are looking at the number of times an event occurs in a fixed interval of time. For example, if you are looking at how many phone calls are received per hour, there we use Poisson distribution. But if you are looking at number of successes, we use binomial distribution. Poisson distribution in terms of public health, you may use an example of number of new cholera cases reported in a district in every week. That in every week, how many cases have been reported. Then you say that what is the probability that 50 cases will be reported per week? There we use Poisson distribution. Binomial distribution, you're looking at the number of patients who recover or don't recover from a disease. What is the probability that 7 people will recover out of the 12 if we have used this drug? What is the probability that 90% of the people will recover? That is, we use binomial distribution to calculate those probabilities. The central limit theorem, we have already mentioned it. It states that the distribution of a sample means. That means if we make many samples from a population and we measure their means, that is what we are calling sample means. The distribution of sample means will approach a normal distribution regardless of the original population's distribution, provided that the sample size is sufficiently large. And here we mean more than 30 items. So it says that if I'm making samples, maybe I go and measure 30 people. I get 30 people, I measure the average weight. I go and I measure, I count another 30 people, I measure the average weight. Another 30 people. That the averages I'm making, they will approximate to a normal distribution, irrespective of whether the data was skewed, whether the weight in the population is not normal. As long as I'm getting their sample means, they will approximate a normal distribution. That is what the central limit theorem says. So it depends on the sample size. If the sample size is less, then the central limit theorem cannot apply. Then now we go to the interpretations. That was just an introduction to the interpretations. When you have made biostatistical tests, there are things we are measuring. We usually measure confidence interval. Confidence interval is an estimated range of values that is calculated from sample data, and it is associated with a confidence level. When you say that 95% confidence interval, what it simply means is that which interval of ranges do we believe, are we 95% sure that the value we are looking for is lying there? If you are measuring the average weight of people in Uganda, and we have made samples, and we measure the confidence interval, we say that our confidence interval, 95% confidence interval, that our interval is between 80 kilograms and 90 kilograms. It means that we are 95% sure that the average weight lies between 80 and 90. But it does not mean that there is 95% chance that the average weight lies there. So many times when you're measuring confidence intervals, we are trying, because usually it is hard to choose one figure. Presenting a confidence interval is better than presenting just one figure. So as I've said, 95% intervals, we are confident that the true average blood pressure, we are 95% confident that the true average blood pressure lies between, maybe, let me say, if we are looking at a drug and we tested a drug which reduces blood pressure, and we want to determine what is the average reduction, at what reduction does this drug, at which rate does it reduce the blood pressure. When we present it as a confidence interval, we say that we are 95%. If our confidence interval is 10 to 15, it means that we are 95% confident that average reduction lies there. That is what it means. It does not mean that there is chance, because the average weight actually is one figure. It is just that we are not sure what that figure is. So we present an interval and we show our confidence that our confidence is 95% that it will lie here. That is what this illustration is showing. So probably this is a couple or what? So they were looking for a place, and the man told the girl that I got the instructions from my statistics professor, and he was 80% confident that the true location of the restaurant was in the neighborhood. He didn't say that there is 80% chances that is the neighborhood, but that is confidence level. What is our confidence interval? The confidence interval usually calculated like that. Though the formula may change, we calculate a certain mean. Many times we get a confidence interval for our average, that is the mean. We want to get an interval where our mean, we believe the mean of the population will lie. So you have got the mean of your sample. You want to use it to measure the interval where the mean of the bigger population lies. So this is what is being represented by this P. So you get the sample mean plus or minus, this is the confidence coefficient, and it is determined by the confidence interval, then times standard deviation out of root of n. This formula inside here is for binomial distribution, because in binomial, variance is p times q, which is p times 1 minus p. So square root of variance gives you standard deviation. That is why in other formulas, you find that instead of using this, they will put standard deviation out of square root of n, but it is the same thing. So it depends on your interval, that we want our confidence interval, say 90% confidence. Then you go to the table and say 90%, what is our z coefficient? It is the z coefficient is 1.645. Then after picking it, you come and substitute it here, 1.645. Then times, they say what was the probability of success? Probability of success is 130 out of 296 times 1 minus that probability of success divided by square root. Then you get the confidence interval, meaning after calculating, we say plus or minus. So it is either above or below. This illustration can show it well. We're saying here where the white part, which is unshaded, is. This is our confidence interval. That we are 90% sure that the average, the mean will lie between here and here. So we are trying to get the lower limit and upper limit. That's why I say plus or minus. So these are commonly used values of Z intervals. But there are many software that calculate these things. What is important is the concept. Knowing this formula, we know that 95% confidence interval for the true proportion is given by, this is the mean plus or minus z at 95% square root of variance out of n. Then you substitute that. What is the sample mean? We calculated the sample mean was 0.45. What is the z coefficient from the table? 1.96. What is the probability of success? You substitute. Then you get the lower boundary and the upper boundary. So from this confidence interval we have got, it means we are 95% confident that the population mean lies between 0.422 and 0.478. How do we interpret confidence intervals? We have already talked about that. So the confidence level reflects the long-run success rate of the method. Wider confidence intervals indicate more uncertainty. Is if you say that I'm sure that the average body weight in Uganda lies between 10 kilograms and 100 kilograms. That is, it means you are not so certain. Like you have given a very big range. But the smaller the confidence interval, the more certain you are. Meaning also the more accurate is the method you are using for measuring. So all of these things can be affected by the data collection tools, the study designs you used in research. So that is confidence interval. Now we go to the hypothesis testing. This involves setting up two opposing statements. There is the null hypothesis, which suggests that there is no difference, and the alternative hypothesis, which suggests that there is an effect or a difference exists. Of course, null means that it is not valid. Many times in biostatistics, we collect data and use statistical tests to evaluate the evidence against the null hypothesis. We have this example. Maybe we have made a new biofertilizer. The null hypothesis, after applying the fertilizer and we get the results, the null hypothesis will suggest that these results we have got, they are not due to this biofertilizer, probably due to other factors, or even the fertilizers didn't have any effect. So that is null hypothesis. We suggest the status quo, that what has happened either out of chance or because that is how it happens. So we collect data and we want to prove that what happened is not a result of chance, but it is because of the effect we applied. In clinical settings, you applied a drug. Then you got the test results, you recorded them. You want to test the hypothesis. Are the results I'm getting due to the drug I've applied, or it is just random chance? That is what we mean by testing a hypothesis. So the results are often expressed with a p-value. And we are going to talk about later what the p-value represents. But in brief, it is a probability value, which helps to assess the strength of the evidence. Many times we don't judge using eyes. Maybe you've got a drug which reduces blood pressure. Just because you're using your eyes, you're seeing the values have reduced. We have to use statistics to say that is the difference statistically significant? Is it due to chance, or it might be due to just chance and variation? That is why we test hypotheses. So we can briefly describe null and alternative hypothesis. A null hypothesis is a statement of no effect. There is no difference, there is no relationship. If you're looking at association between smoking and lung cancer, null hypothesis suggests that there is no relationship, meaning the results we have got, they might be due to chance. So we have to disapprove it. And if we fail to disapprove it, we cannot reject it. So as I said, it represents the status quo or the claim. Sometimes some people make other claims and we make research to disapprove those claims or to prove whether the claims are true. So probably someone made an analytical or an observation study and suggested there is a relationship, there is a positive relationship between age and blood pressure. When I'm making another research, that will be my null hypothesis. Or usually a null hypothesis is something standard. Maybe the news provided this, they presented that the average body weight in Uganda is 70 kilograms. That is the null hypothesis. That is the status quo. That is what is standard that has been presented. Then I'll make a test to provide an alternative hypothesis that actually the average body weight is greater than 70. So I have to make a test. I make statistical tests to show that there is a statistic significance and difference from the null hypothesis. So the null hypothesis is a statement that contradicts the null. They have to contradict. The null and alternative hypothesis are contradictory. Before we do that test, we have to understand that two types of errors we can make in hypothesis testing. Number one is a type 1 error and number 2 is a type 2 error. A type 1 error is also called the alpha error. This occurs when we incorrectly reject a true null hypothesis. Incorrectly, meaning it was the null hypothesis was saying there is no difference. Then we make a test and we say that there is a difference. There we have made a false positive. Meaning we are presenting something as positive that the drug has had effect, yet it had no effect. That is a false positive, is the type 1 error. So the probability of a type 1 error is set by the significance level. Meaning usually the significance level is what we use to determine the errors. Significance level you can say at 5% significance, then alpha will be 0.05. Maybe 3% significance, whatever the significance level is, then we use as a critical point to measure whether we have made a type 1 error or not. And it is also the one we use to assess the p-value, whether there is statistical significance or not. A type 2 error occurs when we incorrectly fail to reject a false null hypothesis. Probably we made tests and we say that actually there is no relationship. Meaning you made tests, you are showing that, then you say that the drug has no effect, yet it has an effect. So you have presented a false negative. You have said it is negative, yet it is false. That is a type 2 error. An illustration is what we have used here. A type 1 error is like telling a man that you are pregnant. First of all, he's a man, meaning a man cannot get pregnant, and you tell him that they are pregnant. That is a false positive. A type 2 error is telling a pregnant woman that you are not pregnant. That is a false negative. So those are the two errors we can make in the hypothesis testing. That leads us to the last part of this video. How do we make inferences? How do we make sense of the sample? Or how can we use a sample to make conclusions from a bigger population? Of course, we are going to be applying hypothesis testing. The main test we use is the z-tests, t-tests, and the chi-squares. Mainly we use z-tests and t-tests. Both tests assess whether a sample mean differs significantly from a hypothesized value or another sample mean. When we are testing a hypothesis, we use the sample mean. So you have measured your sample. What is your average blood pressure? It is this. Then we say that is this blood pressure statistically significant from the known average blood pressure? You have made a drug reducing blood pressure, you go to the average. So we get it and say that what is the known average blood pressure? That it is this. Then we want to measure using statistics whether the difference is significant. What we mean by statistically significant, we want to show whether it is not by chance. So sometimes we use a hypothesized value, which is a value which is known. Maybe you read from the news or from documents, you get the known value, then you compare it with the mean you have got from your sample. So we use this mean and the hypothesized value to make these z-tests and t-tests. Sometimes you have made two samples. You are doing a clinical trial. You measured the blood pressure before giving them the drug, then the blood pressure after giving them the drug. Or you are doing a randomized control. You give one group the drug, the other one you give it a placebo. Then you measure their sample, mean blood pressure. Then you want to use a z-test or a t-test to see is there a statistical significance between these two values. Can we conclude that the drug has had a significant impact on their blood pressure? That is what we are dealing with in hypothesis testing using z-tests and t-tests. Z-tests are used when the population standard deviation is known or when the sample size is large. Meaning if I'm comparing body weight, for me to use a z-test, I must know the standard deviation of the body weight in the whole population, which is in most real world scenarios not ideal. And we can only use it when the sample size is greater than 30. So we assume that if the size is large, even if we don't know the standard deviation, we can use a z-test using the central limit theorem that as the sample size becomes large, the sample means the sample mean will approximate the population mean, like they become close to each other. So meaning we can use a sample mean in a z-test. That is if the sample is large, but many times a t-test is preferred because for it is designed to be used when the population standard deviation is not known. That is why they are more commonly applied in real world research. When do we use each? I've already mentioned that. You start with the first question from this flowchart. Do you know the population standard deviation? Yes. If I know it, then I ask myself, is the sample size above 30? Why? Because I need to choose. First of all, because I know the standard deviation, I have two options. I either use a z-test or a t-test. But I will only use a z-test if the sample size is large. But what is common in both is a t-test. It is not whether I have the standard deviation on the population standard deviation or not. Whether the sample size is large or not, a t-test will apply. So it is preferred and is the more common scenario. Formula of a z-test is very simple. So remember using z-tests when we know the population standard deviation, because we use the standard deviation of the population in this calculation, but in the t-test we use the standard deviation either of the population of the sample we have calculated. Then we have to know the hypothesized value. What is the average blood pressure according to the documents, according to the available data? Then we compare it. What was our average blood pressure from our sample? Then we put in the t-test. N represents the number of observations. That is the number of samples. How many people did you observe? Then you put in the t-test, you get the Z statistic. Then the Z statistic will be used to get the p-value. Z-test, we can use this one, as I've already said, but we can also use Z-test for comparing two groups, but when the population standard deviation is known. So I get the mean of one group minus the mean of the second group, divide by square root of standard deviation of the population squared, divide by the number of observation plus population standard deviation of the other one. Important to note, you only use population standard deviation, not the sample standard deviation for the Z-test. Then we go to the t-tests which are most applicable. They have three types of t-tests: the one sample t-test, the independent samples, and the paired samples. One sample t-test is most common because you have carried out the experiment, you want to compare with the hypothesized value, meaning a value which is already known, a value which has already been determined. For example, they have said if you are testing if a new drug's average effect differs from a standard baseline, here you will come and use a t-test. So in a t-test, we use the standard deviation we have measured from our sample. So it is not more, you don't need to look for the standard deviation of the population. The t-distribution is better because it accounts for the added uncertainty of estimating population standard deviation from the sample. Because we don't know the standard deviation of the population, in t-distribution, in the formula of the t-test, the population standard deviation is just estimated. So in a t-test, there is more there is accountability for the uncertainty. Because we don't know the population standard deviation, it is accounted for in the t-test. So these are the two sample t-tests, either for the one sample or the two sample. The two sample will depend, are the samples independent or the samples paired. So here we have the observed mean of the sample, x bars representing the mean of the sample, minus the assumed mean. Assumed mean may come from the hypothesized value. Then divide by standard deviation of the sample, divide by the square root of the sample size. Then it is two sample t-test. We're having mean of one sample minus the mean of another sample divided by square root of. So you need to pick the values from your calculations, values from the question if it is a test, then you apply it in the formula to get the t-test statistic. The t-test statistic and the z-test statistic, we use them to get the p-values. And it is the p-values which we use to determine the significance. In independent samples, we are assessing if there is a statistical difference between two independent groups. The data from one group must not influence the other group's data. So, for example, if you are looking at two drugs which we are given to various patients, Then you say, is the average recovery time different for patients who received drug A compared to those who received drug B? The groups are different and they are independent. What is happening in one group does not affect what happens in another group. It is used when the population standard deviations are unknown. Of course, for t-tests, population standard deviation is unknown. The test determines if the observed difference between the sample means is likely due to a real difference in the population means. That is for independent samples. The means of the two samples, standard deviations of the two samples, and the number of cases for each sample from those two groups. And lastly, the paired samples t-test. It is used when observations are applied or dependent. Examples include measuring the same individuals before and after an intervention or comparing twins. This one is usually used in randomized clinical trials. Before you do tests on these people, you have to first measure their initial values, then you apply the drug or the intervention, then you measure again. So you are using the same group, the variability is the same, then you compare the results before and after. So since the samples are the same, then we use a paired samples t-test. It is more powerful for detecting small effects since it controls for individual variability. So what changes in the t-test for dependent samples? We use the sum of the differences. The sum of the differences instead of the sample mean. You see where in the independent t-test we are using the sample mean here. But in the dependent samples or the paired samples, we make a table. The illustration is here. You make a table, you put the results before and the results after. Then you get the difference between these two. Then you sum all of them and divide by the total number, by n, the total number of observations. So this is the calculation here we made and I got -2. After that, we have to substitute it here. So I get -2 minus the assumed mean, maybe from the hypothesized value, from the standard values, divided by standard deviation out of the square root of the sample. So from this example we have used here, we are calculating t, which is the test statistic. We got -2 from the difference minus the hypothesized value, in this case was 0. Or from the higher standard values, the answer had to be 0. So you subtract it, divide by, we got standard deviation divided by root n, which was 1.2, divided by root 8. The value we got, we divided it from this and we got the t-test statistic. So as I said, the t-test statistic and z-statistic are used to get the p-values. There are softwares that can give you the p-values from those statistics right away. Just get the z-statistic, you fill into the software, it gives you its p-value. Or it can even tell you whether it is significant or not. So how do we interpret them? We use the p-values. A p-value is a probability of observing data as extreme as or more extreme than our current sample data. Remember where we started from, we said that as we start the experiment, we assume the null hypothesis is true. So we have got our data. We are saying that smoking, okay, let's say we are saying that this drug is causing an increased blood pressure. Then we want to use z-tests and t-tests to determine what is the probability, the p-value I'm talking about, what is the probability of getting values like we got if it was due to chance. I don't know if you are getting it. So maybe yes, we have observed that blood pressure has reduced because of the drug. in this hypothesis testing, we want to get a p-value, a probability of getting the results like the ones we got if it was due to chance, meaning if the null hypothesis was true. Meaning if the p-value is very small, there is very little chance that the results we got are due to chance. That is why we use p-values to state the significance. For example, at 5% significance level, the alpha will be 0.05. So meaning, even if we get a p-value which is small but greater than that, we might say there is still a chance that these results are due to chance, not due to the drug we applied. But if the probability of getting the results we got is very small, it means it is very unlikely that the results we have are due to random chance, meaning they are due to the drug we applied. That is what a p-value means. So a small p-value, which is usually less than 0.05, that is at 5% significance, indicates strong evidence against the null hypothesis. That since our p-value was very small, then we have strong evidence that the null hypothesis does not apply. So if the null hypothesis was saying that there is no effect, then we take it away and we say that there is likely effect. Remember, we are dealing with probabilities. So we use words like likely, unlikely. Yes, if a large p-value suggests weak evidence against the null hypothesis, but it does not take it away. It does not tell us the probability that the null hypothesis is true. So if we have a p-value greater than 0.05, we say that we don't have enough evidence that chance didn't contribute. Meaning we may not say that the drug has not have an effect, but still we cannot say that it is the one that caused it. The evidence is not enough. That is why I say that if p-value is less than alpha, we fail to reject the null hypothesis, meaning the null hypothesis will remain true until proved otherwise. So this is the illustration that if we are assessing, we have made a Z test. We got the Z statistic, we used it from the Z table and we got the p-value. Then we found out that the p-value is lying in this range. Where you're seeing the observed data point, that is where our significance level begins. So at 0.05, it means 0.05 starts from here up to here. So for us to reject the null hypothesis, our p-value should be smaller than this, meaning it should lie in this region, not beyond this. So this normal distribution is saying that if a value lies in all this white region, it can be due to chance. But we are only confident if it is in this green region. The interpretations, we use these graphs, a null hypothesis. If our mean is less than the 5% significance level, we take the hypothesis. We take the alternative hypothesis if our mean if the value that we have got is greater than the value we are looking for. So these are representing various things. That in this normal distribution, for the null hypothesis, we say that actually this illustration is summarizing how we write hypothesis. Because in the calculation of hypothesis testing, you have to first state the null hypothesis and the alternative hypothesis. So in such a case, if we are looking for a probability, maybe if the null hypothesis is saying that the mean is less than the hypothesized value, but for us we want to prove that the mean is greater than it. So the null hypothesis will be that the mean is less or equal to the value. Then our alternative hypothesis, which is HA, will say that the mean is greater than the value. From this, if you want to prove, if maybe the hypothesis, the status quo says that the mean is greater than this, then for us we want to prove that the mean is less than this. In other words, these two things have to be opposite, as we said. From this illustration, If there is a certain hypothesis that says that the mean is equal to this value, then for us want to prove that the mean is not equal to that value. So you have to first state them. HO representing null hypothesis, HA the alternative hypothesis. Then you start the calculation of the Z test, get the Z statistic. Z statistic is filled into the software, you get the p-value, then you use the p-value. Say since the p-value is less than the significance level, the null hypothesis is not true, or the alternative hypothesis is likely to be true. Since it is not, we cannot reject, we have failed to reject the null hypothesis. Effect size. After calculating the p-values, the p-value will only tell you whether the test is statistically significant. And as I said, statistically significant means it is unlikely due to chance. But it cannot tell you how big or how strong the effect is. That is for these continuous variables. So usually after calculating the p-value, if it shows us positive that yes, it is likely that the drug is statistically significant, then we go ahead to calculate the effect size. That what is the effect size of the drug? How strong is the effect? Why? Because sometimes even a statistically significant, the p-value may show statistical significance, yet in practicality, it is not meaningful. An example can be you tested a drug, and usually large sample sizes can give you statistical significance even with small effect in reality. So you have made a large sample size on your drug. Then the test has showed that the statistic drop in the blood pressure. But you go in reality, the blood pressure has dropped by 1 millimeters of mercury. Then you ask yourself, if someone has 140 millimeters of mercury, dropping it to 139, is it practically meaningful? That is why we calculate the effect size. What is the effect size? However much it is statistically significant, is it practically meaningful? And there are two tests you can use, either the Cohen's d, where we use the mean, or the R square, where we use variance. So in Cohen's d, we get the difference between the mean. Yes, we have calculated the sample mean between these two groups, and there is statistical significance. Then we go and we get the difference. What is the effect size? So, but the effect size is very small. So even if it is statistically significant, it has little impact. But if the effect size is large, then it is a better power over test. After you have carried out either Z test or a T test, usually we ask you calculate its power. The power of a test is the probability of that test correctly rejecting a false null hypothesis. Meaning, if the test is showing you statistical significance, you want to say what is the probability that this test will reject the null hypothesis, and the null hypothesis is wrong. So in other words, giving you the probability of giving you your desired result if the null hypothesis is wrong. How it is calculated, you get 1 minus the type 2 error. Remember we talked about the type 2 error. Type 2 error is about false negative. Type 1 error is about false positive. So here we are applying the other complement rule we began with, that if the probability of happening is beta, the probability of not happening is 1 minus beta. So if the probability of making a false negative is beta, then the probability of rejecting a false null hypothesis will be 1 minus beta. It can be influenced by sample size, effect size. As the sample size increases, the power also increases. Meaning the bigger the sample size, the larger the power of a test. Researchers aim for high power, e.g. 80%, to confidently detect true effects. Meaning, even if it has showed statistical significance, if it has power less than 80%, it is not considered to be reliable. It has been a long way, and now we end with a chi-square. The chi-square is we use it for categorical data. These z-tests and t-tests, we use them for continuous variables. But chi-squares is used to test association, whether there is really association between whatever we are trying to compare. So we mainly use it in categorical data, and we use it in contingency tables, meaning you went and recorded smoking, lung cancer. How many have the disease? How many smoked? How many had this? How many smoked? So we want to apply a chi-square test to find out. But is there an association anyway? Even before we start counting odds ratio, relative risk. For it will show you, is there an association? And how do we do it? We compare it to the hypothesized values. For example, you calculated that the rate among smokers in lung cancer, what is the 30? We got 30 out of 100. Then we go to the hypothesized values. Maybe go to the research data which has already been recorded. Then we get the value from the research data when we start comparing. So we use this chi-square, meaning you need data which you have observed and data which is hypothesized. Or if you're using a chi-square to compare two tables, you're having data from one group and data from another group. You want to show, is there association? Is the association significant? So even before you start calculating odds ratio, relative risk, association is tested using a chi-square. It compares observed frequencies in categories to frequencies expected by chance. Meaning it is also a tool used to rule out chance. What if our results are due to chance? So I get the results which we expect if it was just chance. Then I compare them to our observed frequencies. Put in a chi-square. I get p-value. Then I conclude whether it is statistically significant or not. An example is that we're having females and males. What we are seeing in black, we calculated the numbers. That among the females, those for deposit they are 18, those for liter they are 7, the total is 25. The males 42, here 33, total is this. Then we get the totals. This is a contingency table. Now we want to apply the chi-square, which is represented by x squared. So we need to get the chi-square statistic. You put it in a software, it gives you the p-value. Then the p-value is tested at a certain significance. Maybe 5% significance, you get 0.05. Is it less than 8? If it is less than 8, then okay, it is not due to chance. There is an association. Then there you can continue to measure how big is the association, either using odds ratio or relative risk. So we need, the ones you're seeing in red are the values which we are expecting. If you fail to get them from data, they can be calculated using this same table. So the formula is we add the squared differences of every cell you are seeing here, meaning for all these boxes, divided by the total. E starting for the total, which is this 100. Then you add all of them, that is the Z statistic. You put in the formula, you get the p-value, then you compare. Here it has been calculated. The ones we got from our experiment, we got 4 males, 2 females. The ones we got from both males and females were 3. Those from males, females, from both. So we first get the difference, meaning I get 4 minus 2.1. Then I square it. After squaring, I divide by the total. Divide by 7. Then I get 1.72. Then I get 2 minus 5.4. The answer I get, I square it. divide by 18, I get 2.14. So I do it for all the cells here. Then after I add this 1.72 plus 2.14 plus 0.74 plus 0.92, then I get the chi-square statistic. Then I use it to get the p value. So there are two types of chi-squares. Actually, there may be three, but you're going to talk about two. The chi-square goodness of fit test. This one, we use it to determine if the observed frequency are significantly different from the expected frequency. So we are looking at goodness of fit, just like the example I've given. This is used for a single categorical variable. You have used one variable, you have recorded your data. You want to compare it with the hypothesized values which are already standard to see if there is statistical difference. The expected frequencies can come from theory, past data, or a uniform distribution. Then after, this test is to evaluate how good the fit is between your observed data and the expected. Are they fitting? Are they associated, or they are statistically different? This table, actually this illustration here, is just showing what we are showing here, that we are having your observed answers. Observation 1, observation 2, observation 3, observation 4. Then you get the expected one. Maybe you get a table from past data. Now you want to apply a chi-square to show that the results I've got are different from those, to see if there is association or not, or to see if there is statistical difference. Of course, if there is statistical difference and you get the p-value less than the significance level, then we say that there is difference. But if the p-value is greater than the significance level, then we fail to reject the null hypothesis. Chi-square test of independence. There we are testing between two variables which are independent of another. In chi-square goodness of fit test, you are having one variable comparing it with past data. But now here we are looking at two variables. So you're having one table and another, and though the concept will remain the same, the calculation. So one table, we take it to be the expected, another one take it to be the observed. Get the differences, square them, divide by the totals, add all what you have got, use it to get the statistic, get the p-value, get the determine is it less than the 5% significance. That is how we test for independence and association using the chi-square. The data must be in form of counts. That is why I said that the chi-square is best for discrete data. That is not dealing with the points or continuous data, and can also be used for categorical data. The interpretation, we have already talked about it, and maybe to briefly go through it. Perform a chi-square test, get the chi-square statistic. Use the chi-square statistic to get a p-value. Compare your p-value to your chosen significance level. If it is 5%, it will be 0.05. If your p-value is less than it or equal to it, you reject the null hypothesis. But if it is greater than it, we fail to reject the null hypothesis. This one already illustrated it, that your p-value must lie in this region for it to be considered significance. In this significant region, the blue one. If it is beyond it, we cannot reject the null hypothesis. These are some calculated values. What I didn't mention in chi-square test, for you to get the chi-square statistic, you need to have the DF, which is calculated. You get the number of observation or the samples minus 1. Meaning if you observed 8 observation minus 1, you get 7. Then you use it with the chi-square statistic you have, you go to the table to get the p-value. After getting the p-value, like the first example, you have 0.023. You say that p is less than 0.05, so there is no significant association. So there is a significant association, sorry, because this is what we desire, something less than the significance level. But in this another example, it was greater than it. So it says since p is greater than 0.05, so there is no significant association between the two variables. That is how we conclude. So thank you so much for this journey. The key takeaways: biostatistics is a vital tool for understanding health data. Data types, the measurement and study designs are foundational because the bias from these study designs will influence your data, and any changes in data will affect the inference making. The statistical inferences, you may fail to reject the null hypothesis, yet it is correct. The p-values and confidence intervals help us to interpret findings. So you have measured the blood pressure, present it in form of a confidence interval. 95% confidence interval, we are 95% sure the average value lies between here and here. Always be critical consumers of medical evidence. Biostatistics is essential for understanding, identifying trends, evaluating interventions. Interventions have been made which have to be evaluated whether they are effective or not. So we use those tests and drawing reliable conclusions. Thank you so much for watching. So you feel free to share if you liked this video.